Alright, now let's talk about another reason in this video for being able to use units and make calculations, and that is estimating things. When you go out into the real world and you're working for a company or you're doing research or whatever, often you can be involved in situations where the stuff that you're working on is actually dangerous. Unlike in a classroom situation where the teacher has taken the time to ensure that all the power used is sufficiently small that it can't hurt you, that the voltages can't hurt you. In the real world, if you're working at a company, for instance, as an engineer, or even if you're not an engineer, you're just a technician working, the company is doing something. For instance, it might be using electricity in order to machine a material at FMC. Or it might be at another company where it's using energy in order to get oil and gas out from under the ground. This stuff that it's doing has the potential to do work, we're going to find out, and that work can be bad. And that work, if it's done wrong, can kill you. So when you're walking into a situation, how do you know if the situation is safe? What can you do? If you reach out toward and point toward a particular device, will you be electrocuted because the voltage can actually cause the current to jump from the ground to your hand? Or is it such that it's totally safe and you don't have to worry about taking special precautions? Here's where units can help. So let me give an example. There's a 30 microamp current that's flowing through a 22.7 kilo ohm resistor in a circuit. This could be a circuit, for instance, in the back of a radio or something. Is it dangerous to place your hands across that resistor? Now, if you don't know, the answer is you shouldn't be messing with it, but this might be part of your work. Well, the 30 is neat and the 22.7 is neat, but the fact is I can answer this question largely just from looking at this microamp, this kilo ohm, and make this calculation in a fraction of a second in my head without doing any detailed calculations with a calculator, and it will tell me it's safe. Now, of course, I do have to know some physics, and we'll learn later on that there's this formula that says that the voltage that one puts depends on the current times the resistance. Okay, well, the voltage here depends on a microamp, that's 10 to the minus 6, and a kilo ohm, which is 10 to the third. Well, minus 6 and 10 to the third is 10 to the minus 3. So we're talking about a millivolt. Now, 30 times 20, I can do that in my head. 2 times 3 is 6, and I have 10 and 10 is 100, so that's 600. 600 millivolts. This isn't even 1 volt. This isn't the equivalent of a battery. A 9-volt battery I can take and stick across my tongue and it won't hurt. We're not even talking about one little flashlight battery that you may pick up on the ends and you don't worry about electrocuting yourself. So certainly there's nothing dangerous here. Being able to walk in and immediately make a snap decision whether something is dangerous, whether the amount of medication is too much and could cause a person to bleed out, or is too little, it couldn't possibly have the effect, is an important ability to be able to do. You don't need to know if it's twice the amount or 3 times the amount, but you do need to be able to know roughly whether it's dangerous or not and what type of precaution and procedures you have to follow. And we get to do that as a scientist by using units. This is the gateway in which we're able to make snap decisions. Even if you don't want to be a scientist, let's say that you're going to end up being a manager. You need to be able, when people bring you a problem, to immediately be able to make a snap decision about whether the project they're proposing is reasonable and it can actually be achieved, or whether it's impossible. For instance, they haven't properly assumed the amount of money necessary, or the materials is too small. Being able to make snap decisions are important because real calculations in the real world often can take years to perform. They often require us to measure things that we don't know ahead of time. And that's going to mean that you're going to have to put in money into the project. And if the project can't even work and you put millions of dollars to find out it can't work, that's a good way to go out of business. So one of the things that doing science enables you to do is numerical literacy, the ability to make quick mathematical calculations. And that's a useful skill for anyone in their future careers. Now, let's take a look at some more things in this area of estimation. And there was a person who was incredibly successful at this. His name was Enrico Fermi. He was a physicist who won a Nobel Prize. He built the first nuclear pile that led to nuclear engineering, was on the bomb decisions for making that. He was great in semiconductors, and most of the things are Fermi equations. Even certain particles are known as fermions because he was so important in this field. He was both a theorist, a great mathematician, and an experimentalist, something really unique in the ability to have specialties in two totally different fields and be one of the world-class people in it. One of the things that he could do really well was to take a look at data, almost any data that people weren't even really sure, and make a rough factor of 10 calculations about what would work. Whether or not, if you set this bomb off, it could set off the entire atmosphere. Whether or not this type of semiconductor could actually produce blue light. He could do these better than almost anyone. He was incredibly gifted. So calculations, when you make a power of 10 estimates, are often called Fermi calculations, or Fermi estimates after him. It was said that there was a pool for the nuclear bomb project at Trinity when they did the explosion about how big would the amount of the energy released by this explosion. He supposedly crumpled a paper when the explosion happened, dropped it, and then wrote the answer to better than 1/10 of 1%. That's pretty impressive if that's really true. Okay, so Fermi calculations. So here's what we're going to do. We get a question like this. Roughly how tall is the Empire State Building? 10 feet, 100 feet, 1,000 feet, 10,000 feet, 100,000 feet? This is what we want to answer. Well, here's a way we could do that. Well, let's see. It's a tall building. About 100 floors. You want to say 50? That's fine. But it's certainly more than 10. We only got to be within a factor of 10. How big's the floor? Well, I don't know. It's bigger than a basketball field. If I look up, I know it's a lot taller than me, and I'm, a little under 6 feet, so it's at least 10 feet. And, of course, there's probably a little bit of concrete and some air conditioning ducts, so let's say 12 feet per floor. Maybe it's 13. Maybe it's 11. Doesn't matter. Rough, close. Well, then that says that thing should be about 1,200 feet. Actually, the Empire State Building's about 1,240 feet. Go find the exact size in Wikipedia. Bottom line is, if you come and tell me that building's 10,000 feet, I know it's wrong. If you come and tell me that building's 100 feet, I know you're way off. I certainly have a rough estimate of how big it is just by roughly estimating the factors that are important. Another one, you're told that there were 960 home runs last year in the major leagues. Is this number reasonable? People often give you numbers when they want to convince you to vote for something politically or something. Is this reasonable? Well, let's look. 960 home runs. How many teams are there? Well, there's a bunch of teams. Let's say 25 teams. There's actually not that many. There's more teams than 25, but that's close enough. There's some players on it. There's 9 players roughly to start. Maybe you got a few utilities. Pitchers don't hit a lot of home runs. Let's say there's 10. 10 players per team. How many home runs does an average player hit? Well, I don't know. Let's say that he hits 10. Now, some people like Bonds may have hit more than 60. Some people only hit maybe 30. Well, it turns out 10 is not a very good home run hitting. A really good player is going to hit in the 30s or something. So maybe you don't like 10, 15. I'm happy enough with 10. That's, if anything, probably on the low side, I think. Now, you notice that I have to know something about the sport. This is true about anything in your profession. You got to know something about your profession. If you're a shipbuilder, you got to know something about ships. And you take and use this with the math. So the players kill, the teams kills, and I'm in home runs. 10 times 10 is a home run. 25, that'd be 2,500 home runs. And I'm thinking that that's probably on the low side. Well, this thing isn't even, half that. So that says the average person's on the average team across the board, all their hitters are hitting on average of 5 home runs. Well, if one guy hits 30 home runs, that's good for the next 6 people. So this seems way too low. By the way, it turns out there are more than 25 teams. So 960 seems too low. So a person brings this thing into my office in a snap decision. I look in and I say, nah, what you're proposing doesn't seem reasonable to me. I'm not going to spend a lot of money, a lot of time. I can very quickly make a snap decision about what is reasonable or not reasonable, what is safe and not safe. Now, you may think this only happens in science, and in your notes I put a little discussion of the fact that millions of people's lives were affected in the Civil War. There was a guy by the name of George McClellan. George McClellan was a brilliant railroad engineer, and he actually led the Union forces. And he had a campaign in the peninsula following a battle in which he was attempting to move up the peninsula to take this city of Richmond and end the war. And he was told by a guy, Pinkerton, who formed the Pinkerton Protection Agency, that there was a Confederate army of 200,000 men in front of him. And this was based on the number of wagons that Pinkerton saw, how many people he saw walking on the street, how many dogs, horses, how many pigs in the camp. I mean, he didn't actually see any of these people. He had this math formula, and he was using it to make policy. And McClellan believed it and immediately entrenched and didn't command to go forward. Well, there were several reasons why you should have known this couldn't possibly be true. For one thing, there was 100,000 men, according to Perry, that he had. So unless he was facing around 100,000 men, he should be able to take him. But, this says he's outnumbered 2-1. Okay. But the Confederacy were also trying to protect Mississippi and Tennessee during the war, and they had about 60 to 100,000 men that fought in a battle called Shiloh. They had another 30 to 60,000 men over in the Shenandoah that had been engaged with another army. And not only that, but they had an army, a fairly large army, that had fought up in a battle called Bull Run, which was on the order of another 60,000 people or so. So when you start adding that with some other armies, you get a rough estimate that about 400,000 men were there. And that's not counting the fact that he wants to add another 100,000 here. So that's like 500,000 men. Well, even if you gave a great liberal thing, there's at most 500 total men in the entire South. So you're saying that the South has already brought together 8 to 10% of every person in the entire country and put them in battle. And they did this with no army in almost no time. That is highly unlikely that they could have done this in less than 1 year. The North couldn't do that. What was the real truth? So, do I say that it had to be wrong? No. What I say is he should have thought about this and went and tried to get better data. He should have figured out whether it was true rather than just believing any number handed to him. In reality, he was facing 30,000 men, and he had 100,000 men, and had he attacked, he would have ended the war and saved potentially millions of lives. Instead, he entrenched, he didn't fight. Eventually, another army was moved in front of him, and the war went on for almost 4 more years because of his failure to do this. You must take a look at numbers and ask yourself, is it reasonable? Does this make sense? And not just say any number a calculator or someone gives you is true. It has dire consequence in the real world, and it won't do too well on your homework papers in this course either. All right, that covers this unit. Make sure you've read all of Chapter 1 on your book on units, and we will then move on to other consequences and important things like vectors.